Okay, so as I was saying, we will do a practical lecture today, like analyzing some data set coming from an article. The article is in this link. I will copy and paste it in the chat. And they study what is called VOT, which is vocal onset time. Uh, I'm not a linguist, but I've read that it's a phonetic measurement that it is like, I don't know, maybe I haven't reviewed. Let's open the wiki page, which is, by the way, here.
Yeah, it's also
So,
important for native for speakers. It's important to distinguish voiced and voiceless consonants. So the time when the vocal folds start to vibrate, if it's too short, if the time is too short, then it's perceived as voiced, and if it's long enough, it's just co-articulation of the next because of the next vowel. Yeah.
okay. That makes sense. Much better explained than I would have done it. And yes, the dataset is actually contains, of course. Let's download it. So we will see it. Also, it contains a column that tells you if the word that they use is voiced or not. So let me first review a little bit. So. Maybe the data is on this GitHub page of the author of the paper. So I will also put it in the chat. So, and there is also there is a book of him about about regressions in linguistic data, which is very well explained. So this is a reference for linear regressions. Um so let's see how the data is. So to to skim through the data, there are various commands. One is head, which shows the first um, 6 or 7 rows and the column names. One can also put column names of vote and have the same, or less similar output. So the column names are like speaker, which is there are some speakers here that they record like a word that they utter, and there is like okay, the gender of the speaker, the phonetic, the letter. If it is the vocal onset time, so the time in I don't know, milliseconds probably, or I don't
Yeah,
know
it's
really.
milliseconds. Yeah, it's always milliseconds. Yeah.
Okay, perfect. And the logarithm of the vocal onset time and the voicing, if it is voiceless or voiced or voiceless. Okay, some linguistic columns, so where the stress falls, and many stuff. So to skim through the data, you can also use like skim from the skim package, the skim function, which like gives you also some details, some statistic on the columns. So, for instance, the column vocal onset time has 0 missing values. So the complete rate is 1. The mean is 33 milliseconds. The standard deviation is 26, and so on. The percentile, they plot the percentiles and the histogram. And this is for the numeric variables. Then there are also the categorical variables, like the speaker, the word. So there are no missing data. And here they put the me. Okay, they put some data. And okay, you can see how many speakers are there. Like there are 20 speakers. Because actually I've read a little bit that article and it says that it was they were like the speakers were like in television, like I don't know, the Big Brother, if you have ever seen it. I'm not a fan of it, but there are some
No,
people.
no, no,
Uh,
big what?
Sorry, I didn't hear you.
Yeah, I didn't get interview like for some show you
Yes,
mentioned.
yes, the show Big Brother, like they are in a room, and the article I think planned wanted to see like if the vocal onset time changed through the time they were in the house, and so there are very few speakers, 20, and so actually the data here is not independent because many speakers are repeated. So if you know that maybe each speaker has naturally a vocal onset time due to its to its I don't know individuality. So we can see here with this command like we group by speaker the data and we summarize the number of each group. So how many uh, data there is for each there are for each speaker. So and we select like the speaker. We want simply to have like the most in data as independent as possible. So we throw away. We take only one person, and this person is like the one with most. No, we take. I think I have taken like Mohammed simply because I don't know randomly or Mitchell. Ah no, sorry. We take the speaker with most observations because we have more data. So Mitchell. Okay. So there are okay. There are some questions that we can ask. So before looking the data, we should like look at the column names. I mean, actually, we should choose the column names when doing the experiment because we collect the data. But here we have the column names. So let's see if we can like get some I don't know some idea of what to test. Like as you said, it depends on the voice. So the vocal onset time depends on the whether the consonant is voiceless or voiced. So for instance, mm, okay, let's first select Mitchell. So we filter the data and select Mitchell. Okay, so with this simple, it's very easy to work with. The advantage of working with R is that um, this working with data, filtering, selecting columns is really easy. Then we can look at the columns and choose like something to test, like the vocal onset time should depend on this voicing parameter. So, and let's do a regression with that. I mean, so how can we do it? So the first thing to test is the vocal onset time depends on the voicing parameter, voicing feature. So let's test it. So what is the regression model now? The regression models uh, the vocal onset time, which is a numeric variable, is equal to a linear function, so beta 0 plus beta 1. But now we have to encode the variable uh, times some encoding of the variable voicing. So how can we do it? So we have this voicing variable can be either voiced or voiceless. So we have only two possibilities.
So 0 and 1.
Exactly. So the intuition tells us that, I mean, it's one possible way is to put to define this dummy variable. It's called here we put a question mark, and the question mark is equal a dummy variable, dummy version, variable version of the column of the variable voicing. So we can do it really easily. So we take, okay, we save this data frame about Michel in both vocal onset time of Michel. So we have it saved in memory, and we define, we take the variable voicing, and if it is equal to voiceless, so this command gives us a vector of, it puts us true or false whether the row has a voiceless or a voiced consonant. So a uh, true is like 1 and false is like 0. So we could take like is is voiced, the variable is voiced, can be defined in this way. We assume that this vector of zeros, trues or true and false, is a numeric vector. So this command will put us a 1 if it is true, or 0 if it is false. So actually is voiced, here we should put voiced. So let's see if it is something I didn't do any mistake. So yes, 0 tells 0 is equal to a false, and false is equal to this condition being false. So it's equal to a voiceless consonant. So having defined this variable here, which is we put a 0 or a 1, depending on whether the consonant is voiced or voiceless, we can do various, we can, let's attach it, this column to the data. So vocal onset time of Michel, and we mutate it. So we take the data, we mutate a column, and we define it to like, we can also simply bind the column, so it's much easier actually. Cbind vocal onset time Michel, and the variable is voice. Now we have a new column with, okay, we don't have it. Okay, yes, we have it. Okay, okay. Okay. By default, a stable puts value as the name of the column, but it should be is voiced. So probably we should do like this. Yes. So now these two, the is voiced variable and the um, voicing variable tells us the same stuff, but the voicing is numerical, and we can do the linear regression. So we can take vocal onset that we can assume that the vocal onset time is equal to beta zero, an intercept plus a slope times this variable is voiced. And we can do a linear regression actually, so we can estimate this beta 0 and beta 1, and the code is really easy. So let's save this data frame into augmented vocal onset time of Mitchell. So, and we can do the linear regression. So linear model, so the method is that we use is the least square method. So it should be the default method, but I don't remember it. And we like yes, probably it's the default method. So and we have to predict the vocal onset time using the variable is voiced, and the data is the augmented vocal onset time of Michel. So we are trying to predict the vocal onset time using this variable. Well, is voiced is without a capital letter. And okay, we obtain this this estimates our intercept and our slope. So actually, what it tells this graph is that the vocal onset time, this output is like 57 milliseconds, 0.15 plus beta 1 times the variable is voiced. Now, do you have any interpretation for this beta 1? So, like in this case, minus 43.64. So, the variable is voiced that we have defined is equal to 1 if the consonant that they are pronouncing is voiced or not. So, what is 57.15 in this case? So,
Not that clear for now, yeah.
sorry?
Not that clear for now.
Okay, thank you. So we have made this assumption that the vocal onset time is equal to to a number beta 0 plus beta 1 times this variable is voiced, which is voiced can be either 0 or 1. because we are trying to predict the vocal onset time using the fact whether the consonant is voiced or voiceless. So now this variable can take only two values, 0 or 1. 0 if it is voiceless, 1 if it is voiced. So this vocal onset time, we have only two predictions of this vocal onset time. One, when is voiced is equal to 1, 0 when is voiced is equal to 0, so when it is voiceless. And this command simply, this linear regression, estimates our coefficients. So we using some method that we defined in the previous lecture. So in this case, beta 0, so the vocal onset time, do you have any interpretation for this beta 0 and beta 1? So, for instance, if is voiced is equal to 0, so we can make some guesses like, is this a good, are these good coefficients like 4 minus 5 plus 3000 is voiced? Is this so why it is not a good guess for these coefficients, because why? The question is why.
Yeah, especially if beta 0 is a negative number, it would be very strange to have a negative number for a positive value of time.
Exactly. So is voiced, for instance, the vocal onset time in this case for a voiceless variable would be like -5, which makes no sense. And the vocal onset time, so beta 0 is actually, you can interpret beta 0, it's actually when you substitute 0 in this variable, it's simply the vocal onset time for a voiceless variable is equal to beta 0 plus beta 1 times 0, which is beta 0. So beta 0 is the estimate for the vocal onset time of a voiceless consonant. Estimation. Well, probably it should be, okay, probably it's the converse, because in this case, beta 0 is, okay, beta 0 is bigger, so I guess that for a voiceless consonant, it is better. So it is shorter, this vocal onset time. So probably is the converse. So it's voice.
That's completely all right. For a voiceless, it should be longer.
Okay.
Yeah,
So
because otherwise it would be perceived as voiced. Yeah, because your vocal folds start to vibrate too early, then it's voiced. Yeah.
okay. Thank you.
What's a bit strange for me is that the prediction we have, it kind of gives us only two possible values, like 57.15 and it'll be like 13 point something. Yeah,
Yeah.
we kind of don't see any variation, but we have this variation in the data. So we kind of wanted to simplify the overall image we have, right?
Yes. The idea of doing this is just a guess. Of course, you cannot. So everybody. So if you take some individual, you make him pronounce some sentence, it won't be precise that number. But the fact is that we use this variable to give a better prediction rather than estimating, like we could guess the vocal onset time without taking into account anything. We simply uh, we simply do the mean of the all vocal onset times, and we say, okay, this is our estimate. But here we are doing a better estimate for each value of the consonant. But yes, it's still an estimate. It's not certain. And the idea is that the uncertainty, like the randomness comes from other variables that we didn't take into account. I don't know, like um, I don't know the length. I don't know the structure of the mouth of the guy that is speaking, which could be, I mean, could be a variable, but you don't know. You cannot take it into account. It's too difficult. Or like the language, the school in which they went, the teacher, maybe they I don't know if the teacher from the elementary used longer vocal onset times. I don't know. But and that variability that we cannot take into account is like the noise, but we can give an estimate. So, but as you said, okay, beta zero is the estimation for the vocal onset time for a voiceless consonant. And we can also interpret beta 1, as you said, as the difference uh, is equal to the vocal onset time for is voiced equal to 1 minus beta 0. So beta 1 is the difference between our estimates. Um, Okay, so I mean that's the point is that we can make a better estimate, and we actually what we did with the dummy variable, what R does is to do it automatically. So we could have used our initial vocal onset time of Michael without the column we have created, um, simply, and it creates automatically that column. So we can take we can try to predict the vocal onset time using the what was it called, the voice variable. So Michael, sorry, okay. Voice not found. What was it called? Voicing. Okay, the column was called voicing. And it does the same, but in the converse way. So, like now it created, okay, maybe we could, okay, we can try to change here the zeros with ones, so have the same coefficients. Okay, so okay, now we have the same coefficients, and because R does exactly the same, and we can also summarize summarize this model and also plot it. So this is linear model. We summarize this model, and it will take will give us some more information. Ok, no. Summary linear mode, okay, probably. mm, Maybe plot. Ah, okay, linear model was not found, of course. Okay, maybe summarize is good. Was a good. Okay, no, it was summary. Okay, so it gives us some more quantity, like it tells us if this coefficient that we found, beta 0 and beta 1, are significantly different from 0 or not. Like these are it makes a t-test and it gives us back this information. So now a little bit of a comment on this stuff. So what are we doing? We are trying to predict like the vocal onset time. So in this case, it's very easy because we can plot it. So uh, the data is vocal onset time of Michel, and we can plot the points. On the x-axis, we plot uh, the variable voicing, and on the y-axis, we plot the variable vocal onset time, and we can see the on point. We can see what are we trying to do, like we are trying, okay, we can not still see it. No. Mm, okay, so we are trying to predict the y-axis using the differently in each of the two columns. So in the first column, we had like a guess of 14 point something, and on the second, like of 57. So it makes sense. And let's try to plot also a line. So, so I need a numeric variable, and we can also actually use, we can use a geomstat function. Sorry, stat smooth layer, and use a linear model. The method is a linear model, and try to predict the vocal onset time using the variable is voiced. And this should should plot me the line. Okay. Mm, maybe it was. Ah, okay. The formula should be like. Okay, I'm not doing. I start smooth. Um, okay, I did it some time ago, so I don't remember it. Okay, geom smooth should be fine. I don't know why it's not working. Why? Because requires okay. X is because okay, it doesn't inherit from geom point the aesthetics, but from should put the aesthetics on the first line. Sorry, this is really not interesting stuff, but okay. And they didn't plot the line. Why? Uh, Valid type list for the variable. Oh, mm. Well, okay, let's try to plot the linear models simply. It's better. So, okay. Okay, no, this is too advanced. I simply wanted a plot with the line. So I will take geom line, geom smooth line, and I will put the slope and the intercept. So the intercept was equal to 14, something like that, and the slope was equal to 43, something like that. And uh, use the command aesthetics. Okay, so this is our guess. And so actually the point in the middles are really not interesting because we are simply interested in zero and one, in the zero and the one column. So it tells us, but the p-values tell us that beta zero, beta zero, so beta zero is not really important with the p-value, but the p-value of beta 1 tells us that this is significantly different from zero. So it is different from zero, not because of randomness, but because like if we assume that that model is true, then the true beta 1 is really different from zero. So there is a and recall that the interpretation of beta 1 is like the difference between the two predictions. So our predictions differ not by chance, but because there is a real effect, which of course you do linguistics, so you know better than me that the voicing of the letter so has something to do with the vocal onset time. So this is our p-value, and actually, so what are we doing? We are simply so last lecture I wanted to like give you a like some hint that this linear regression estimation is really trying to compute the mean. So if we do the mean of the vocal onset time for voiced variables, for voiced consonant, um, this is simply our prediction, so it's simply 13.51. So we go back here, it was our beta zero, and the other one. So we are simply computing the mean of the two columns.
By the way, can you please show us an entry with say voiced consonant, but the voice answering time more than say 20? The plot shows that there are such entries in data.
Okay, so I guess most of the, so let's try to
It
let's
should be a
do-
concession of two voiceless consonants, but I'm just curious whether it's true or not.
so maybe let's try to we can plot. So for instance, uh, this is our prediction for voiceless variables is 57. Okay, so here we should go like okay, for instance, place the P was had a big vocal onset time, plush, prison. Uh, the one with P's, I guess, they are voiceless and they are
Oh, there it was on the third page, I guess. It was
sorry,
20, yeah, D in do, 20 milliseconds. Yeah, nice, thanks. Yeah.
okay. Okay, with less, okay, they are voiced and they have more than 13, yes, okay. So yes, we did this simple. This is, I mean, this is exaggerated to do a linear regression for this, but it's actually the same. If you remember, we had done this test, which like compare the mean of a sample. So you had an hypothesis zero, which was like the mean of the mean is mu zero. The mean mu, you have a guess for the mean, which is mu zero, and a sample taken from a distribution, and the hypothesis zero is that the mean is the guess. And you had an alternative hypothesis, which is like the mean it can be, I don't know, mu is different from mu zero. Actually, what we are doing here is very similar, but now we are comparing the mean of two groups. We are not comparing the mean of a group with some guess. We are comparing the mean of two groups, the first column and the second column. This is called actually the two-sample t-test, which is so what we are doing actually is a two-sample t-test. So we go here and let's recall the code for the t-test. So uh, I don't know if we have like the data, which is the vocal time of Mitchell, and we try to predict both with with the voicing variable, we obtain exactly the same stuff. Now, yes, we should take for the p-values to be equal, we should set like one parameter, so like variance. So, okay, I forgot the name. Well, uh, but equal some, I mean, um, something not really important. I mean, the default values of R usually are the one to take. So the t statistic is 77, and we go here, go back to the summary of our model, and the t statistic is 77. So it is the same, exactly the same test. Now, we didn't do it in lecture. We did this following test. So we have a sample. So the sample in this case would be like the vocal onset times of for a voiced consonant or sorry, vowel, I guess. Okay, and this is the sample, and what we knew was to perform a t-test using this sample and a guess for the mean. So our guess would be like the mean of the voiceless uh, of the mean of for a voiceless onset the onset time of a voiceless consonant. So but this, I mean, if this were if we knew that this guess were the true mean of the hypothesis zero, this would be like a t-test, a one sample t-test. But here we have two samples, so we there is also a t-test for instead of replacing of taking one sample and comparing the mean with a guess, you take two samples and you compare their means. So this is like what we knew, but in this case, it is much better to do a two sample. I mean, we are in the framework of a two sample test. So is it clear? Like, I mean, this is simply to say that some tests, so the linear regression, like kind has every test that we made, we defined the mathematics not really different, it's the same, but the way of narrating it is different. So, but here, for instance, it is a t-test. And in fact, you don't care about the line here because it makes no sense to compute the line at 0.5. I mean, it's not. So you can compute it only at 0 and at 1. So here we are in the context of the t-test. So this was simply to give you an example of practical example of what you can do with data. So in this case, the result is not surprising at all. But let's try to, I don't know, to see if other variables like can influence the vocal onset time. Or maybe let me first tell you something that you have to keep in mind. So if you have three, so here the voicing parameter could be like, can have two values. So what happens, what would have we done if it had three values? So
we could just take three values like 0, 1 second, and 1, for example.
that it's an idea, but it's actually that is what you shouldn't do because it's what I wanted to say because you are making assumptions using that encoding. So the wrong encoding is like I don't know. There was this. Okay, let me give you an example. So there was this drama corpus. So the corpora with a lot with dramas from different the corpora for different languages. So there were like dramas that were comedies, tragedies, and tragicomedies for the German dataset. So we have a variable which can take three values, so comedy, tragedy, or tragicomedy. And let's try to see how can we encode them, and let's try to predict like the length of the drama using the genre of the drama. So the column normalized, so let me plot. So, well, there is the play name, okay, this is not important, the title, okay, the subtitle, well, the source, different kind of data, and yes, there are the number of words, which can be a measure for the length, that of course, and let me see. Okay, the normalized genre, there was a column. Okay, the normalized genre can take three values like comedy, tragedy, and tragicomedy. So we try to predict from this column the length, let's say what column. Well, there should be like a column called like length. Let's see. Mm, word count. So word count is equal to like beta 0 plus beta 1. Okay, the wrong encoding would put here a variable like x, and x is equal to 0 if it is a comedy. 1 if it is a tragedy, and 2, for instance, if it is a comedy, a tragicomedy. So, why it is wrong? Well, because the word count for a for a comedy, which is this one, is equal to beta 0. Then the word count for a tragedy, which is for x is equal to 1. It is beta 0 plus beta 1. And the word count for x equal to 2 is equal to beta 0 plus 2 beta 1. So in practice, like the difference in length between tragicomedies and tragedies is the same as the difference in length between tragedies and comedies.
And if we say move to negatives and take -1, 0, and 1. Will it raise the same problem?
Yeah, because like for instance, if
Oh, yeah. Yeah, I see
uh,
now. It'll still be beta 1. Yeah.
yes, there is a relation between, so beta 1 can be interpreted as the difference in the estimations between tragedies and comedies and between tragicomedies and tragedies. So this is something that, so if you use this model, you are assuming something that probably isn't true. I mean, but I mean, you can do it, but you have to do it, so providing I mean, reasons. In this case, I don't see any reason why it should be, and in general, it is not the case. So the encoding, it is, we have to create two variables actually. We can create, like the variable is tragedy, is comedy, the variable is tragedy, and the variable is tragicomedy. And we can do it simply, so these variables are one if the drama is a comedy, and zero otherwise. So is tragedy is the same with the tragedy, so equal to one if the drama is a tragedy.
So we kind of compare one value to all the rest 3 times, just changing the value we compare.
Um, yes, but the point is that this variable is determined by these two variables. So actually, it's like two times that we. So
Oh, yeah,
because
right. Yeah.
yes, so
If it's not the first two, then we can simply deduce it from the, well, just
exactly.
logically,
So
mathematically.
if it is not a comedy and not a tragedy, it is a tragicomedy. So we need only, so from n variables we need one less than. So if we have three possibilities, we need two dummy variables. This is the dummy encoding. It's called of a factor. And we can actually define it. So we can take, we can define the column like is tragedy by taking the German drama corpus and taking the column normalized as genre and say when it is equal to a tragedy, the play. And we impose it to be a number as we did before. So this is like one if it is a tragedy, zero otherwise. Okay, and so on with comedies um, and tragicomedies. Uh, so we can take these ones and like
Oh, you've lost an I in tragicomedy.
thank you. It would be like a null vector. Okay, thank you. Cbind is so the corpus ger and is tragedy, is comedy, and is tragicomedy. And like we can see that we created okay different numbers of those. Comedy, yes, okay, probably tragicomedy. Okay, now we should see some output, I guess. Yes. And we substitute instead of the factor, these three new columns. But as we noted before, like one column is too much, is like too much. But now it's like okay, there is some error here. Comedy, tragedy, tragicomedy. Um, mm, mm, mm. Um, there is some error here, but I cannot spot. Okay, with there are capital letters in the name, so okay. So now we go. Now we see that okay, no. So we substitute the gender of the play with numerical variables, and the numerical variables are indicate if it is a comedy. For instance, this is a comedy. And as we spotted before, like the third column actually depends on the first two, because if it is a tragedy, it is not a tragicomedy, so it is zero. If we see a one on the first two columns, then the third one is zero. If there is, if there are two zeros on the first columns, then the third one is a one. So we need only to do this, to use these first two columns. And actually, the model is the following. In this case, we replace the model with the number of words, like the word count is equal to beta 0 plus beta 1 times the dummy variable is tragedy, for instance, plus beta 2 times the variable is comedy, for instance. And this is the model, like we can replace that model with this one. And now the usual interpretation is that beta 1 is like the difference between the prediction of word count for a tragedy and a tragicomedy, because beta 0 is like the estimation for a tragicomedy. And so we can do this, and beta 2 is like the difference between the word count in comedies and in tragicomedies, and we can do the usual stuff. So the data is equal to so we can take our augmented, let's say, augmented gel corpus, and we can do this linear regression. So the word count, we predict the word count without the capital letter. So using the normalized genre, which was is tragedy plus is comedy, and we will get some results. So word count SP with okay, we can do this, and okay, we can also take, let's call it model one. We can take, and we can do actually it is the same. I mean, what we did is actually useless because R does it automatically, because if we take the word count and we predict it using the normalized genre, it gives us the same, it does exactly what we did. So let's try to do it. Okay, I don't remember precisely how the column. Okay, I need to go back and okay, normalized genre. I guess I okay. Data normalized genre. It's exactly the same, and we can see it from the summary of the model one and of the model two. So the first one, the intercept is okay. There are some. Okay, he used the variable is tragicomedy. So it's like maybe we can use it. So instead of is comedy, is tragicomedy. Tragedy and tragicomedy. And in this case, they are exactly the same. I mean, they were also the same, but now we can see that they are the same coefficient, the same p-values, t-values, p-values, and because they are exactly the same stuff. And the fact that these coefficients are significant, like at least only actually, so only the tragedy coefficient is significantly different from zero. So the true model, if the model were true, this is a strong hint on the fact that the beta 1 that we have written here is different from zero. So, I mean, because this is an estimation of the true beta beta 1. So in this case, it means that, so recall the interpretation of beta 1. The interpretation of beta 1 is like the difference between our predictions. So it's like saying that the predictions are different from each other, not because of the randomness of our corpus, but because really in tragedies are, I guess, longer than comedies. So let me see. Yes, the coefficient is positive, so tragedies are longer and significantly longer. Instead, for tragicomedies, there is not enough data to say anything. And we don't care about the p-value of the intercept. Of course, it is different from zero because dramas have some length, so which is different from zero. So this is trivial. This the first line. Uh, okay, so do you have questions concerning this dummy encoding for factors with three or more levels, like when you can choose between not only two alternatives but three or four?
For me, it looks clear.
Okay, that's good. Okay, we can. Okay, maybe what I wanted to do next. Well, I wanted to try to to introduce. Actually, I could go on a little bit with theory because there is something to be okay. So the usual stuff about causality and so what can we say about causal relation if the slope of the linear regression is different from zero? So like in this case, uh, so maybe so let's take a 10 minutes break and then let's do some theoretical stuff, but really not mathematical, but more like philosophical. So see you in
Okay.
10 minutes.
Okay.
Have any questions concerning the previous part, that task? If not, let's go on with um, like
Sorry, can you repeat the last sentence? It was not loud enough. Yeah.
No, if not, I go on with what I wanted to do in this part. So sorry, there was no information in this sentence. Uh, so okay, what I wanted to do in this part is like let me see where I was. Okay, it was okay. We did some linear regression using factors as predictors, which is, I mean, it is a way to do them. To do this linear regression, we try to predict a numerical variable using some predictors. Now, if it uh, if it gives us a positive result, the linear regression in terms of testing, it tells us, for instance, okay, where I was here, for instance, it tells us that this slope is significantly different from zero. Well, in particular, it tells us that the vocal onset time depends on the x variable, so on the variable is voiced. Now, the fact in statistics is that a dependence doesn't mean causality. So, and I wanted to simply to state better this fact. So, if the slope is significantly different from zero, the y variable depends from the x variable. So stochastically, it depends stochastically, so statistically, sorry. So, and so I want to refresh what those statistical dependence mean. So it doesn't mean causality, because if we have some data done in this way, like, I don't know, the number of shark attacks, so we record them like in the I don't know, the numbers done, there could be numbers done in this way, like are the numbers of shark attacks in like in July. Then there is the number of ice cream sold. Uh, which could be like normally distributed around, I don't know, it is summer, so they sell like 1,000, sorry, the number of ice creams of data is 5, but the mean of this normal is equal to 1,000, maybe, let's say. And this in summer. In winter, the shark attacks like are much more. I mean, there are basically no shark attacks, so there could be like something like this. And the ice creams in winter like less popular. I don't know why, but yes. So there is some. It could be like some data done this way, like the mean is 500. So and so these are the same variables. Simply the observation is taken in different times. So we can take the total number of shark attacks and collecting them together, like concatenating shark attack winter and shark attack summer, and also concatenating the number of ice creams sold, ice creams that are sold in winter, and the ice creams that are sold in summer, and we can plot them like
So what it says essentially is that there is no any causal relationship, but there is something behind that makes those two events go hand in hand.
yes, exactly, exactly. And in this case, okay, you see the variables like that something behind is like you can think that it is a variable, like the variable is summer, like the variable is summer. If it is one, so if it is summer, then the distribution of both change, but they are independent in this. I mean, I've chosen them independently, like, but they actually depend from by this something behind, which is the variable. This variable is summer. If it is summer, they are independent but distributed in some way. If it is winter, they are independent but distributed in another way. So if you observe a variable, if you observe the number of ice creams that are sold, you can like get information on this variable is summer. So if there are like only 14 ice cream sold, then maybe it is winter, and then probably I would guess that the number of shark attacks is lower than if I didn't have this information. So they depend statistically, but they are, of course, not causal. So this is the point, and this is summary is like it's called a confounding variable. Confounding variable. So this is let's simply plot also the linear, so the regression line, or maybe let's take let's try to predict the number of shark attacks from the number of ice creams sold, and we see that we will see that probably it is significant. So we try to predict shark attacks using the ice creams. The data is the one I plotted below, and you see that okay, it is significant actually. So there is a correlation. This tells us only that there is the line, the slope of the line that fits the data is significantly different from zero. And recall that this is the same as doing the correlation test, like core test. I simply we did it 2 weeks ago. So let's see if it is true. So the p-value is 0.0012. Yes, it is the same. And the t-statistic, it is 4.62. So we are doing exactly the same mathematics behind, but this tells us that this test doesn't look for causal relation, but only for correlations. And this is a little bit sad because in science you want to do like what the ultimate goal is to discover some causal relations, but this is an empirical relation. I mean, already I don't know. Linguistics is much more complicated than I don't know. There are a lot of variables to take into account, and even finding a correlation is a result because it means that there is some mechanism behind that. In this case, it is this confounding variable, but there can be the situation can be much more complicated, of course. And for instance, at the beginning of statistics, um like everybody is used to smoke, and like data was starting to being disclosed on like the relationship between smoking and other some illnesses, and but so people were saying like that correlation is not causation. So if you plot the data, you should provide me a hint, like something, not simply data plotted in a graph to say that smoking is bad for your health. So what can we do? How can we check for causal relations? So there is, okay, there are, we can do some various different stuff. One is like it's called randomized controlled trials, which is really nothing that I think you can use in linguistics. What you can use is like the adjusting for confounders. So in this case, what you do basically is to give two guesses of causal diagrams. For instance, for the smoking, like there are like expectation, life expectancy, versus cigarettes per day. So if you plot something like this, you will see that, I don't know, some data like this one. I don't know. Is equal to, I don't know, okay, the cigarettes per day, let's take something like a uniform between, I don't know, 1 and 10. And life expectancy, let's say 90 minus 3 per cigarettes per day.
Let's take cigarettes per day 20 and life expectancy 73.
Okay, yes.
Yeah, closer to the life in Russian.
I mean, I didn't put I wanted to be optimistic, but I didn't put the units of measure, so I could be, I don't know. Well,
10 cartons a day.
yeah. Well, let's say in this way, and plus some noise, so a normal, I don't know, I'm taking 20 observations, so let's take some variance, and let's plot this data. So, and now one could say, okay, causation is not correlation, so what do you want? Okay, so what can we do? The fact is that we can like test the causal diagram. So like the first one is like cigarette cause some like, I don't know, disease which I mean which lower the life expectancy. Well, can you find an alternative explanation for this like graph here? I mean, in the same fashion as the one for the sharks. You should find like a variable that maybe influences both.
Heart failures, the chance of a heart failure, the chance of getting cancer.
Okay, but this would be like yes, this is still in this direction, hints into this direction. I wanted to like to justify like this graph in another way that makes you like I mean, which will make cigarettes not responsible for this. I mean, which for this could be like simply a correlation, not a causation. So um, I wanted to find a variable that influences both cigarettes per day and life expectancy, so that this diagram, this data does not come from causal relation. So
Those who
you,
smoke
you
cigarettes are usually those who take risks, hence their life expectancy is lower.
okay. That could be an explanation. Also, I don't know. There could be like I don't know. See, maybe smoking is due to stress. So stress, I don't know. Yes, but stress or risks. But I mean, stress maybe is um, which like makes you like both smoke more and but also I don't know, drink more. And drinking is bad, so this causes a lower life expectancy. And what you can do so with linear regressions is to check whether this one or this other diagram is more likely. So I mean, and how would you do? Like, so how would you take some data to decide for like the question of deciding whether the first diagram, so this is the first causal diagram, this is the second. Uh, so we want to collect data to decide which one is more likely to be true, is true. So if we want to disprove the second diagram, we should take like the same data, but at the same level of so we should select people that drink the same and but smoke different kind no I mean smoke a different number of cigarettes but drink the same and see if you still see this effect, then the first one should be true. If instead you see some flat line for people that drink with at the same level, maybe then the second one is a better explanation. The fact is that it is so it is difficult to select people that drink the same amount of so we should ask a lot of people, then dividing them in how many in how much they drink, and then computing this diagram for every group. So what one can do is to take this variable and add it to the data and do a linear regression with all the possible explanations. So also with this drinking level. So I don't know. Probably we could take like some data like cigarettes per day. So the first diagram would correspond something to something like I don't know, glasses per day probably is like something like I don't know, an exponential random variable parameter. Okay, we were taking 20 observations. And then the life expectancy could be like something like 75 minus 2 times cigarettes per day, minus 3 times drinking glasses. This is an explanation that is like confirms the first diagram. Instead, like something that would not confirm the would be for the would confirm like the second diagram would be something like the cigarettes per day are this one, like then if you smoke more, probably you also drink more, so we should have something like glasses per day is equal to cigarettes per day plus okay, plus an exponential. Something like this. And then the life expectancy depends only on the alcohol that you consume. So it is, okay, here I should put also some noise that accounts for the other variables that we are not taking into account. So and here we are assuming that it's something like 75 minus glasses per day plus some noise. So, and we can try to plot, in this case, there is no effect, no direct effect from the cigarettes to the life expectancy, but if we plot it, we plot like the cigarettes per day and the life expectancy, we still see kind of this, we should still see, okay, some correlation. So let's see if it is sufficient to claim that is significant. So we need to do to predict like the life expectancy using the cigarettes per day. Okay, here there is no effect. Okay, valid life expectancy. Let's see. Okay, I need also to make a summary of this model. Okay, here none of them is significant. Well, uh, because okay, mm, cigarettes per day. Why am I? Okay, no, this is not the model. Okay, yes, now it is. Sorry, it is significant. Okay, we see this picture. We go and see, okay, the data looks a little bit correlated. So we go, we perform the test, and it says that, okay, the cigarettes are correlated with the life expectancy, but I gave you the data, and actually they are not causal, because if I increase the cigarettes per day, well, because they actually uh, the formula that uh, from which we calculate life expectancy depends only from the glasses per day and from some independent variables. Then the glasses per day are influenced by the cigarettes per day via the stress confounding variable. But it's not a direct causal relation in this case. And we go back also here where there is actually this causal relation, because I put in the formula for the life expectancy this cigarettes per day term. We go here, we do the same plot. We use model 3 for this. And of course, this will be even more significant, I would say. This is the plot. And cigarettes per day is significant. But now the first diagram is true. So so if we are only given with the data, how to distinguish these two variables? So what are we saying here? We are saying that life expectancy is equal to some beta 0 plus beta 1 times cigarettes per day. Well, do you have any suggestion on how to choose from how to do?
Well, the most intuitive for me would be just try to change the values and see what changes on the plot. Like, let us change the amount of glasses per day and see whether something changes, or let us change the amount of cigarettes as we did already.
Okay, that's true. That's correct. But we have to. So here we know that if we collect data, okay, we only look at this plot. So we can only have access to this data. So here we know that if we see some guy which smokes more, maybe probably life expectancy is, we would estimate a smaller life expectancy. Then the question is why? And there are two different explanations, and there is this variable glasses per day. So, and the idea is to that this slope that we can see from the data is due to that. We want to check if it is due to that variable. So we should look at people that drink the same amount of glasses. So we should remove the data here from people that we should simply keep compare people that drink the same level and see if the slope remains or not. Now, we don't have enough data to do that. So we simply take a multivariate model and we add a variable here. So we take a life expectancy. So yes, we make vary also the classes per day. So we want to expectancy, so to predict the life expectancy using beta 0 and beta 1, so cigarettes per day. But now we also take this beta 2 glasses per day. Now, like the idea is that if it is due to these glasses, then now if we add this variable, beta 2 will be different from 0. But beta 1 will be not significantly different from 0 because if the second explanation is true. So if the explanation, this is true. Otherwise, both will be like significantly different from 0. So we can simply add this predictor to the model. So we can take the first one was model 2, and we add as a predictor classes per day. Okay, I cannot do in this way. So data equal to so I copy and paste all this code here. Maybe let me save the data into that to a variable also. And let me also add the glasses per day variable. So this was the model in which we don't take into account the so it's called okay, here I'm okay, maybe let's take some okay. Now here so cigarettes per day it should be significant, but not because of causality, but because of this confounding variable. So yes, we see that no, here we don't see that it is significant. The p-value is not really not. Maybe we should increase the effect. So like let's simply be a little bit more, put a bigger effect. So yes, now it should be significant. Okay, no, there's something wrong with it. Ah, okay, because I'm really okay, here clearly there is some effect. Why is not significant the p-value? Mm, Hmm. Ah, okay, I'm using another data, not data. Okay, sorry, that was my bad. Uh, okay, now it should be significant, but not due to, yes, not due to causality. So we add to this model this new variable, and now should be, we should spot that it is actually due to the drinking habit. So the reduced life expectancy. So let me, so let me see. Now, this is the summary of the model without the glasses, and it is significant, but because we didn't take into account the confounding variable. Here, we take into account the glasses per day, and this is significant, but the coefficient of cigarettes per day is not anymore significant. So this means that this would mean we have found a hint for the other diagram, the one which explains through stress the correlation. Instead, if we take the same code, but for the model in which there is a real effect of cigarettes per day into the life expectancy, we go here. Where was it? Here. Uh, and we add also the model 4 in which we also use the glasses per day. Now, still, we can see, okay, this negative slope now is due to a real effect, and we can see that the coefficient, okay, not here, okay, this is the real effect, the model, let's see, the model 4, yes, we try to predict life expectancy using, okay, no, I didn't add here. Yes, I did. Okay. Um, okay. Yes. Here there are. Well, cigarettes per day is not anymore significant. Why? Okay, because I used. Sorry, I was here. Okay. Um, and here I didn't actually. I didn't add classes per day into the model. So I add it and okay, let's see. Well, cigarettes per day is still significant because I built the data in that way. But for real data, you could look for confounders using more data, doing a bigger a regression with some more components, and check that still it is significant, your variable. So in the first case, we would say that the second diagram is more likely to be true. In this case, it is more likely that the first diagram is true, like this one, because cigarette is still significant. So this is what you can do. It's called adjusting for confounder. Simply, you take data also on the confounder you think is plays a role. So you have a guess, you take data and you use a linear regression. So that's okay. Maybe I can try to use the code to like to plot like a 3D do a 3D plot, which is quite nice actually. So I had written it here. Maybe instead of copying and paste it, I can simply like I mean, okay. So there is this plotly library which uses which can do 3D plot in a very interactive way, and it's nice. So here there is an error on the y variable and the x variable. So I should take because I have like have other variables defined. So let me see if this plot goes through. Yes. This is because I like kind of introduced without mentioning the multivariate using trying the linear regression using more than one predictor, so a multivariate linear regression is really the same, but let's visualize it. So you see there are some points and you want to take a plane that fits them, and a plane has um, this let me so a plane has this structure, so it is beta 0 plus beta 1 like the variable z is equal to beta 0 plus beta 1 y x plus beta 2 y. So a multivariate linear regression is the same as a bivariate linear regression, but now there are more than one variable on the x-axis, and visualizing it is like I mean like a line, but I mean if you go like this, like a linear regression, take these variables, but if you go like this, okay, this is I mean, it was a little bit theoretical, but it is necessary to know it because it is necessary to have in mind that you are doing like empirical relations, and you may wish to be more precise by taking some more variables into account and deciding which one really influence. I mean, it's something you learn with experience. It's not, there is nobody tells you the code with which the data is generated. You should find it. I mean, try to make your own models, see more data, see which data is more it's more useful, and then see if the data, if your model for new data works in a good way, because so I mean it's more like trying. There is one needs more some practice to work with data. So and okay, correlation doesn't imply causation. So what can be the last topic? I mean, yes, probably we could like either try to go back to the initial example, which was this one of the voice onset times, and try to, I don't know, use more predictors. I don't know, for instance, what are the name, what variables are there? Well, there is also the mean of the speaking rate mean. The gender, the speaking, okay, I don't know. Probably the speaking rate mean influences also the vocal onset time, or also the stress, or the I don't know. Or the frequency. I don't know. Let's try to do it. So let's try to explore this data. By the way, when you have some data, you want to explore it. You kind you are losing. So you look at your data and you find like some. You make a lot of tests and you find like some variables which have some interest. So this is like a common stuff to do. You look at the data and you want to see something on there. But once you see it, I don't know, you do many tests and then one gives you a small p-value and you say, okay, I found some effect. Okay, true, you have found some effect, but you also did a lot of tests, and maybe this effect that you find is due to randomness because you perform like 10 times a test, different kind of test. Eventually, you will get a positive result by randomness. So you can find, for instance, correlations between a lot of stuff. Like there were correlations like between earthquakes and the Oscar, I don't know, the year in which Nicolas Cage won the Oscars. Like there are a lot of correlations which are really due to randomness. So if you look at the data and you do many tests, you have to be aware of that you did that and you found some effect maybe that is due to randomness. So the idea is that then you have to be able to, when you have some new data, to see again that effect. So to reproduce your experiment. So that is important. So when you look at the data, okay, you are doing something that everyone does, but if you find an effect, you have explored your data, and you need to reproduce that effect with using some new data. So, or you can like lower your p-value, but using some corrections. But I don't know. This is a point that should be a little bit clear because it's like for like deontology, because if you do many tests and you report only the positive results, then you are like doing not the best thing. I mean, you shouldn't do that. But apart from that, so let's try to explore the data and to do some more tests. So we have, let's see, like, you know, let's try to do a linear regression trying to predict the vocal onset time using, yes, the voicing of the consonant and the mean speaking rate. So the speak or no, no the word no, sorry, the corpus frequency, so the logarithm of the corpus frequency. Let's see if this um, if it is significant. Well, it looks as if it is, even by a lot. So let's try to. So I recall that. Okay, well, we have seen that the statistic. What do the statistics here mean? Like the multiple R squared is how much variance you are able to explain. The adjusted R squared is like the multiple R squared, but if you add the variables, you penalize like adding variables that are not really predicting. So this multiple R squared really increases while you add variables. But maybe you add simply some noise. For instance, I can add here some noise. and try to predict the vocal onset time using also the this noise. And we see that like the R squared, the multiple R squared has, okay, maybe we cannot see it from here. So let me call this model 1, and let me also use model 2 without, that is the one without the noise. Okay, let's try to see the difference. So the multiple R squared, okay, is the same, but the adjusted has increased in the second in model in the better model has an adjusted R squared, which is better. Now this is because the effect here is really small, but I don't know, I can add some more. So if I add some noise, the R squared should increase because you explain more variance, but the adjusted R squared, no, because it penalizes adding more variables. So it's better to look at it if you have many variables. And to compare the models, you can use the function ANOVA with the analysis of variance. So that means this is simply the last fact. I can compare model 1 and model 2 using ANOVA. It gives me some data. I don't have time to explain it, but I can give you some references. In this GitHub page, there is some good stuff because it is a book done by on on regression modeling for linguistic data. So I don't know. I already shared it with Kostya, but maybe it's also Nagam. So probably it can be useful if I share it again. And that's it. So the thing important about this lecture is that when you explore data and you see which model is better or worse, you are kind of using the data. So you for sure you will see a result, and then you should use that result later to reproduce to see if it is stable, if it is not due to chance. So only that is important. So if you explore your data, you have to keep in mind that you have explored it, you have used it. For instance, here we see that the second model is better because like so this RSS is almost the same, but so this F statistic is not that big, but in that book you can see what everything in this graph means. Let me simply add the functions. There's also this IAC, which compares the models. And I guess the bigger, the better in this case. Ah, no, the smaller, the better, sorry. Okay, maybe let's compare. Model 1 is really not a big model. Really was something spurious that I defined. So let me call this model 1, the one in which I predict the vocal onset times using only the voicing variable. And let's see if what does this have? What does this function tell us? The second model is better actually in this case. And you can see also because this AIC is I guess the last two letters stand for information criterion. The EA, I don't know for which word it stands, but the smaller the better. And there is also the Bayesian information criterion. Maybe let me share the wiki page. Also here, the second model is better. So okay, here is the wiki page. And this again a way to compare two different models, and to choose one which is better. And then with new data, you have to check if it is really a good, stable model. Apart from that, okay, maybe unless you have any particular request, I think that I don't have too much to say more because, well, I could, but it would take some more. I mean, there are a lot of stuff we didn't do. So maybe let me say uh, what we did not do, which was pity. But so probably I will record a lecture on generalized mixed effect models because we missed a lecture, and it is very important in statistics. So in many cases, the data in statistics, sorry, in linguistics, like comes from I don't know, like in this case for the vote, the vote dataset. There were only 20 speakers. So the columns are not really independent. I'm doing a t-test, not taking into account that the samples are not independent. They come from persons that are really from the same person. This generates errors. So the p-values you see are no longer the correct ones. So And usually they are like anti-conservative, this error. So the p-value tends to be smaller than what it should be. So one way to deal with that is to use the generalized mixed effect models, in which the speaker, if it comes from the same person, takes into account that takes into account that. So this is one thing. Then what we didn't do is principal component analysis also, which was nice algorithm. Which is a dimensionality deduction algorithm. So when you have a textbook, for instance, you can define a lot of variables, but then you can define, but then maybe you want to not consider all of them, but only a subclass of them, and this algorithm chooses in some sense the best ones. You can say, okay, I don't want 100 variables, define me from these 100 variables only 2, and it gives you back 2 variables. So it is actually a nice algorithm, this one. And then we didn't do the logistic regression, which is when the predictor is a factor. But this is not really to do the logistic regression. Once you did the linear regression, is really only repeating the same stuff. But I mean, it's super used this logistic regression is super used in general, and in linguistics you have a lot of categorical variables. So I think you will use it a lot if you do statistics. Then logistic regression, principal component analysis, then clustering algorithms, and decision trees and random forests also. So we didn't do this stuff here, but they are not really complicated stuff. Once you understood, you have understood what testing is, then maybe the only one which is a little bit more complicated is the principal component analysis, not because uh, because it's a different kind of algorithm. It's more like it has a little bit of, if you know linear algebra, is really not difficult. But I mean, it's actually a nice algorithm, but it's not. Is the most like difficult part of the course theoretically is like the first one and what we did. So hope that in the future, if you need these other tools or whatever, you will be able to study with not so much effort by yourselves. Okay, and apart from that, okay, I don't know. If you have some more questions, I can answer. Otherwise,